So let's see. First, I will look at Kishore. This is in, yeah. So there are four. Yeah, so 1 million integers. Okay, good, good. So just look at what we are seeing. So input size. So there are four versions of there are bubble sort. The comparison is between four algorithms, four programs: bubble sort recursive, bubble sort iterative, merge sort recursive, merge sort iterative. So and you can see at an input size of 100, there is not much difference between bubble sort recursive and iterative, but merge sort performs better than bubble sort, like almost bubble sort is taking 36 milliseconds, whereas merge sort is taking 11 milliseconds. I'll respond to your question in a moment, Yesh, about space complexity. So you can see that, we didn't go through the time complexity, like why the time complexity part of merge sort. In the next class, we will look into the time complexity of the merge sort. But broadly, what we know is bubble sort takes, so bubble sort, it's a bubble sort. It can take, I don't want to use the big O notation now. It takes approximately, it can take approximately n square time. Whereas, whereas merge sort requires, approximately n log n time. So if you take the ratio between them, n square and n log n, so it will be like the merge sort could be slower by maybe a factor of n by log n, or the bubble sort could be slower by a factor of n by log n when compared to bubble sort. Why it is n log n, we will see in a different class. Let's say if you want to compare what is this n by log n, so I think, how do I compute log n in Python? Import math is, okay. Math dot log n. Okay, now we are good. So like, for example, so speed up is equal to n by, let's say, n is equal to 100. So let's say our speed up, or or merge sort, how well merge sort may perform and compare it to bubble sort is n by log n, but Python is okay, some constant factor, but this is not an indicative thing. So, but what I would like you to see is, like for n is equal to 100, you can see that bubble sort is probably 3 times slower when compared to when compared to merge sort. That's the first observation. Are you with me on this observation? That's first observation. We can possibly ignore what I did in the Python here. I was trying to see, like how n by log n looks for n is equal to 100. But n by log n is not completely indicative, because there will be many constant factors hidden here. Like there will be some constant factor. This is proportionality, right? So this is something like K1, K2, some constant factors hidden. and they will have an impact. So let's not worry about what I did down here in Python. So we will ignore it. Let's come out. But the first thing that I would like you to see is that the method's performance is really good. Are you with me here so far? Fine. There are only 91 students actually. Atharva Joshi. Yeah, okay. Ishika. So Ishika, are you with me? Do you understand what's going on? Okay, good. All right. So now let's go and look at for input size 500. Again, you can see the ratio between now bubble sort and no med sort. This kind of explodes because you can see it is 10 times, possibly 20 times, approximately between maybe 16. Let's do one thing. So how slow it is? 1022 divided by 62. Yeah, 16 times. And then there is a difference in the running time between the recursive and iterative version of the uh, two of bubble sort. And then at input size 1000, what is the speed up? 3752 divided by 132 is 28 times speed up we are getting. See, this is when comparing the runtime of bubble sort and med sort. So this is where asymptotics becomes important, because if the ratio, if you take n square by n log n, if it is some kind of constant, okay, then it's not a problem. But the problem becomes, like when the ratio is n log n. So if the running time of one algorithm is k1 n square and another algorithm is k2 n square, then the speed up is k1 by k2. So as n tends to infinity also, the constant is just a constant factor loss. So it is all right. No, no, MedSort is not pre-sorted individual. Yesterday we have seen, now we take the whole array, we split it into two parts, sort each part separately, each half separately using recursion, and then merge them together. Are you able to appreciate how the time is going? But on the flip side, the recursive and iterative version of bubble sort, it is not, there is some gap, but it's not much. Similarly, at input size, 10,000. So 10,000 divided by 1724 is 5. Yeah, no, it's sorry, 46,519 divided by 1724. It is 267. Oh man. So this is going nuts. Okay, so that's the moral of this story. So I think with these numbers, you will know when you want to use bubble sort down the lane in the future, uh, you will you think twice. But if you see this ratio, how 46 divided by 43, 6230, there is a 5% loss. Yeah, the recursive version is kind of approximately 5% slower when compared with the iterative version. Okay, so like that, the trend is very similar as we keep going, but it becomes interesting when the input becomes 1 million. The recursive version works, but the iterative version works, but the recursive version doesn't work. Why is it? Why is it? Why did the recursive version gave up, but the iterative version? So it is, in order to explain this, we have seen this picture before. So if you look at, this is the memory map of a program. This is the memory map of a program. I will briefly recall how this memory map looks like. So this is, in this memory map, these are the higher addresses. These are the higher addresses, okay, something like that. And these are the lower addresses. And here you have your BIOS or something like that. And then here you have, data section, data plus BSS plus RO data, that is read-only data. And then you have your text section. And then here you have your stack. And then here you have your heap. So what happens is, this will, as the depth of the recursion keeps increasing, the stack keeps growing, it will shoot up here, and no, the stack becomes full, and it will try to override possibly the read-only text section here, and then the system could crash. I think it is milliseconds only. Yeah. So anyway, so are you with me on why you see that it could crash when the depth of the recursion becomes too large? So I want you to refocus once. Those of you, there is some chat going on. I think it's important only, but what I would like you to see is how many of you are with me on this idea that the stack kept growing, and it hit the heap, and then the text section, and then the program crashes. I want you to take a memory map. This is the memory map of the program. This is the memory map of the program. This is the Linux kernel. This is the operating system kernel. And the stack keeps growing, and then it overwrites the heap and take the text section, and at that point it crashes. So one important thing that I want you guys to remember is, so although the time complexity of the recursive and iterative version of bubble sort, if you see, they are the same. The time complexity is the same. The space complexity, if you see, bubble sort, it does sorting in place. That is the input array that is there. That input array, you do in place sorting. That is, you don't use one more array to do in place sorting. But then what happens is, due to recursion, you end up using extra space on the stack, which is not visible to you, which is not explicitly visible to you. So, this is what is happening. It's a very interesting question. The question now for you is, it's not stack smash, it's a stack. So yeah, the question, yeah, Pratyaksh has that question. So how do we overcome this problem? Good question. Okay, so we will see. That's a challenge problem. Figure out a way to sort 10 million numbers. Yeah, so that's a challenge problem for you. So those of you who did this, you can take up this question. So how do we sort 1 million numbers? Because the machine seems to be crashing at 1 million. You cannot store to ROM. ROM is read-only memory. Are you all with me here till this point approximately? If you're all with me, then we can move to the next thing. Gaurav Singh, you're with me? I just want to know, like, get to know the semester is ending. I want to hear from all of you. So I just keep calling you. Uh, how about Janardhan? You're doing good, Janardhan? Okay, great. So now I'll show you a graph with it plotted. I like this graph. Uh, so as you can see, the number of elements increase. Are you able to see the graph here? Okay. So you can see that there is a gap between the recursive and iterative sort that is emerging. This is for bubble sort. This graph is for bubble sort. Uh, so now, yeah, what is it that I wanted to make a point here? Yeah, the question for Kishore and no Lakshmanan and Vedit and some of you who did you measure the time only for the bubble sort function? Yeah, yes, yes. So I looked at the code of Vidit. So let me show the code. So you don't pay attention to everything. So this is these are the line 31 to 33. You get the timestamp on line 31, and you get the timestamp on line 33, and then you take the difference and you compute the time. Uh, so as against this, if you kind of use time instruction, like for example, let's look at some code. Let's say cat where is my sorting program? I want to show one small thing. So I think this sum positive dot c. Yeah. So let's say cat texting dot c cat test max dot text. Okay. So please pay attention now. I just took some program cat testmax dot text, and then the other program is more some positive dot c. This is what it is. GCC some positive dot c dot a dot out less than test sort dot. Sum of positive numbers in the series. I just want to show you something. It's not about this particular program. Uh, some, oh, okay, okay. Yeah, let's not, if INP, does this work? Is this all right? If INP is greater than 0, we just add it, okay? Maybe this should work. GCC, I have appended a non-int at the end. If INP is less than, let me see. If INP is greater than 0, oh, okay, okay. I don't want to do all these things. Huh. Does this make sense now? Okay, so now it will sum the positive numbers. Okay, so let's see GCC sum positive dot C. So one simple way of checking, no, getting the time is like, for example, just by using the time command. But the problem is when we use uh, this approach is, so usually in programs, let's say in the sorting problem, let's not worry about no real user system. Let's just say you focus on this part. Okay, so let's say if you want to use the time command, so let's say you are trying to time your sorting routine. So you do similar, like for example, read input and then sort and then write sorted output. So when you do this, when you apply this time, the whole thing will be considered. This time, this time, this time will all be added up. So, so like say for example, if this takes no reading input, if you are reading from file, if it takes let's say 30% of time, and if it takes let's say another 30% of time, and this takes 40% of time, then 60% of the time is dominated by the read and write, and so and then uh, so let's say this takes 30 milliseconds, and this takes 40 milliseconds, and this also takes 30 milliseconds, and then you write an alternate sorting algorithm. This is sort 1, this is one sorting algorithm, and this is another algorithm, sort 2. uh, so yeah, Prajaksha is a good point, but I will tell what's the issue. So now let's say in the modified, this 30 in the second sorting algorithm, the 30 milliseconds will still be there. These 30 milliseconds will still be there, but let's say this 40 has come to 20. So this algorithm is is giving twice the performance, but if you compute the overall time, this is 80 milliseconds, this is 100 milliseconds. So when we compare this time with this time, you don't get an accurate speed up of the algorithm, because there are other dominant components, that is read input and write output. So it kind of, you don't get a good picture. So in order to get a good picture about your sorting algorithm, so you have to use, separate out the time for this routine, the sort routine, and then compare. This becomes especially important. I mean, let's say this is, let's think of this case. You came up with a brilliant sorting algorithm which reduces this time from 20 to, from 40 to, let's say instead of 20, it reduces it to 1 second, 1 millisecond. Then what will be the running time of the second sorting algorithm? It is 61 milliseconds, and the running time of the the first sorting algorithm is 100 milliseconds. So if you see, if you just focus on the sort, there is a 40x speed up, and but then so the end speed up that you are able to see if you compare 61 milliseconds with 40 milliseconds, it's not that great. Sure, sure. That's the reason why we would like to get this. And also in the general scheme of things, when you are trying to speed up, improve the performance of a system, uh, yeah, so there could be several bottlenecks, and we have to take care of all those bottlenecks too. Yeah, the 60 milliseconds is the same for all the programs. Are you with me on this example? How many of you are with me on this example? So this is an important observation, that even when we get from 40 to 1 millisecond, uh, yeah, if you, of course, Gaurav, so if you take the input from manually, will you be able to supply million inputs, a million numbers in less than a second? No, no, it's not possible. So anyway, so this is one story. Uh, No, that we cannot run a separate program that excludes the algorithms to compute the read-write time, but there are different ways to measure only the performance of each of the routines that are there in your program. So now I will show you one more interesting tool. So it is actually get a more detailed picture of what is happening underneath. Like for example, when we execute this program, the number of actual instructions executed by the processor is, no, this is 7,21,000 instructions. And the number of clock cycles required to execute is this. And there are context switches, CPU migration, and there are a whole lot of other things that you can get by using this what are called as performance counters. This will really help. It's like an X-ray of your program. So this will really help later on in trying to understand what are the performance bottlenecks in your program, and how it can improve. Yeah, so and how where you should focus on in improving the performance of your program. But again, the problem in this perf tool is it is giving at a whole program level. So those are, but if you want to work at a per function level, so you have to use a library called as PAPI, Performance API. Cache grind is for a different purpose, Kishore. Like it's a kind of an emulator, but yeah, you can use cache grind, but it's for a, yeah. You will not be able to monitor large programs because cache grind will run very slow. Uh, but here you execute the programs without interfering the program performance. So this is the API. You may want to check this PAPI API. Those of you who are inquisitive, you can check this API and see. You don't worry about cache grind and call grind, so we'll get to them later. Not later, not even later. We don't need them in this class, okay? Because in order to see how caches perform, and yeah, it's a different story altogether. Okay, are you all with me so far in this class? But I would like you to try out this perf tool and see how yeah, how the code understand where what is going in your programs if you care about performance. There are lots of things you can do using measure many things. You can measure many things using perf too. All right. how will that, well, so uh, it's a good question. Let me see. Let me see if I can. I'm just trying to see power start minus E dash. I forgot the how to get the L1. Yeah, so I'm just trying to see perf list. Yeah, anyway, so what you can do is you can do many things like how well you are using the cache and how things are per stat minus D. Yeah? So let's see if per stat minus D will work. Now I want to have a specific okay, great. Like for example, thank you, Prachesh. Yeah, so you can do many more things, but like for example, you can see what is the in later on in your computer systems organization course, you'll study that all processors have a cache memory, and the key to program performance is utilization of the cache memory. Well, you want to maximize the cache hit ratio. So here you can see that there is what is called as an L1D cache, and the number of the percentage of L1D cache hits is 7.59%, which is very low. And can we do anything about it to improve the performance of the, to improve the better cache utilization, for example? All right. And also you can see there is something called as 0.69 instructions uh, uh, instructions per cycle, but usually we would like this to be greater than one. Okay, at least one we should reach. So we can use all these things to figure out what is happening. And later on, when you are working with really large programs, you will see this page faults also becomes an important thing, because every time there is a page fault, you're going to the disk and accessing the disk, and it will have a huge performance impact. So what happens is your program may have the same time complexity, but you can play around with it and write your code, rewrite your code in different ways, so that the number of page faults will be reduced and the cache utilization will be better, and things like that. So L1D cache stands for L1 data cache. So anyway, so as I said, just think of it as a cache where data and instructions are temporarily buffered. That's true. That's true. We have to utilize the underlying hardware better. That's true. Are you kind of with me on this discussion? I don't expect you to understand the nitty-gritties here. No, no, you don't need to know all these things. I'm just telling all these things to create some excitement in you. I am not sure whether it is causing you excitement or whether you're feeling nervous by seeing all these things. Are you excited or are you nervous? So that's my question. You don't need to worry about all those things about exam and so. But I want you to know, like as computer scientists, and you should know these things. You learn these things in at some period in time. Uh, you learn. So Yeah, you don't need to know. So in any course on programming, you nothing like this will be taught to you. So, but I am just showing you. So it's, yeah. What do page faults represent? So yeah, let's not worry about it. So when you run out of physical memory, you want to go to the hard disk and get some stuff. Yeah. All right. Okay. So let's not get. I think I should stop here. But I'm just giving you some pointers uh, and showing you what is possible. Uh, no, it depends on the disk. On the type, it does depend on the type of, not on the type of the disk, but the page fault overhead depends on the type of the disk that is being used. But the number of page faults itself depends on the amount of main memory that you have and how the program is written. Yes, SSD will have lesser overhead. So if you allocate your swap on SSD, the page fault overhead will be less. Great. So now, yeah, go ahead. I don't know. So you can try to measure it maybe. Uh, okay, I would like to conclude the discussion on this topic for now and take up a new topic. But to summarize, what are the important points, guys, in the, so number one is we were trying to compare recursive, let's summarize the things that we have. I'll just write down here so that those of you who are a bit lost, we can gather together and then we can move forward. So what is the first point? We were compared bubble sort versus merge sort. So here the question is, you can clearly see how the merge sort is performing way better than bubble sort. Yes or no? Are you all with me here? Are you with me on this first observation? Let's take one thing at a time. Okay. I hope you're all with me on this. And this is because of that. So this is why, because this takes n square and this is n log n. And in your data structures course and in your algorithms course, so lot of effort will be spent on how we take an algorithm which is running, whose time complexity is quadratic, that is n square to n log n. Okay, and if it is n log n, can you bring it down to n? So these are the things that you will learn in later courses. The second question is bubble sort. So iterative versus recursive version. This is the second. So recursive version. So the time complexity of both of them are the same, but one will perform better than the other, and then you can see that we have also seen in the recursive version for the large data sizes, because of the stack depth keeps growing. Uh, so you kind of crash the system. I will explain. A good question. We didn't say how, we didn't yet see in the class why it is n log n. Maybe in the next class we will see. But for the time being, just take it as n log n. And here, the reason here is, if you look at the space complexity of space required by the iterative algorithm, let's say if it is capital S, then for the recursive, the space required is k times S, and this k depends upon the size of the activation record for that bubble sort function, because you keep calling it. So every time you call itself, an active and space equivalent to the size of the activation record will be pushed onto the stack. So, and it keeps going. Are you with me here? This is the second thing, because and this k, this is and this will you end up stack overflow will happen, and your system will crash. Are you with me on this comparison, this second thing? We cannot say that the space complexity of the space complexity of even the iterative version is also is approximately. Okay. Number third idea is when you are profiling, so let's say this is your whole program. So let's say when you are working, so let's say if you divide it, if you divide this section of the program into this, you know, this is the, if this is your sort, and even when you compress this thing to almost minimal, you don't get there are other components in the program which will have an impact on the program performance overall. So you need to know, if you are able to measure the time required by this segment separately, then you will get an accurate picture of how your algorithm is impacting the runtime of this section of the program. Are you with me on this third one? That we have to focus on this section of the program. If you are able to measure the runtime here and of the old algorithm and new algorithm, then you will get a good picture on how well you are able to, your new algorithm is able to do when compared with the old algorithm. Okay, this is a very important idea. There is a third related important idea, that is when you have the whole program performance in view, if you just focus on this section, you will only be able to get so much performance improvement. It's so, like for example, let's say no, in your program you know that this takes 40% time and this takes another 40% time. Then can you tell me, if you just focus on this section of the program, what is the best speed up that you can expect? Are you with me here? If you just focus on this percent of the program on this, then what is the best speed up you can expect? So even if you make it equal to 0, there is initially, let's say the program is taking 100 milliseconds. The best thing that we will be able to do is you will be able to bring it down to 80 milliseconds. Yes or no? That's the best you can do. And you compute the percentage, 80, 20 by 100 into whatever, no, that's 20% maybe approximately. 20% is the best that you can get. Are you all with me on this, but the last idea? Okay, good. And then the fourth is the use of the tools such as perf. There are many performance monitoring tools like perf, and PAPI is an API where you have to instrument your code. And then there are some other tools like pin and no, cache grind, etc. You don't need to worry about these things. There will be a course called performance uh, programming for performance. There is a separate course called as programming for performance. You'll get to know some of these things in that course. So finally, so one simple method is what with it did. So you just do know line 31, get time of the day, and no, this is one simple method. I don't know what problems are there in using this approach, but this is a reasonable way to do it. Okay, you're all cool. So point 3 is what I'm saying is, let's say there is a program which has 3 sections in it. One section takes 40 milliseconds, another section takes 20 milliseconds, another section takes 40 milliseconds. What I'm trying to tell is, if you want to, let's say if you're working on trying to improve this section, if you are trying to improve this section, uh, then you need to be able to measure this time separately so that the impact of the modification or improvements in your algorithm will be visible. Otherwise, what happens is the impact of your algorithm, your novel new algorithm, gets masked by the other sections of code that is present in the program. Are you with me on this, Karthik? And to be more clear, like originally, if it is 100 milliseconds, the second idea is even before you go and start optimizing your program, if the original program runtime is 100 milliseconds and you do super duper algorithm and you reduce this 20 milliseconds to, let's say, 0.0001 milliseconds, so then the running time of the new algorithm is 80 milliseconds, then you can see, the performance improvement is 20%. So before you even go ahead and put in the hard work, you can have an estimate that I can put all the hard work, the percentage improvement in the overall program runtime, it will be uh, max 20%. That kind of picture you can get at the very outset. Okay. Joel, Alex. Joel, how are you? Does it make sense or? Okay, so time now is 11:20. Shall we, what do we do? So I have one program I thought we will write together. All fine except 4. It's okay. If you don't get it 4, don't worry. But all I would say is install the perf tool on your machine and play with it. It is fun, even if you don't understand what it is. Okay. So just use the perf tool. Yes. So you don't need to learn a lot. Okay. So that will be a fun tool to use. Okay, then let's keep going. So now we will try to write a program where multiple new ideas will be introduced. One is how to read something from the files. Second is how to, what do I say? Uh, uh, yeah, so how to write to a file, and then, and then how to do heap memory allocation, and so all these things. So what we will do is, no, like time now is, I think it will take half an hour to do this. Time now is 11:25, 11:23. Yeah, 11, let's take 5 minutes break, and 11:30 we will start. 11:30 to 12 we will do it. Is it all right? Okay, 11:25, 11:30, 5 minutes break we will take, uh, and then 11:30 to 12. By 12 we will close the session. Okay, sounds good. Oh, they have a quiz. What time is the quiz? Oh, we have to prepare for the quiz. DS, what is discrete structures? Mm-hmm. You have to prepare for discrete structures. You just go ahead and write the exam. Sorry. uh, okay. So it looks like Okay, so let's do one thing. So in the interest of time, so I think we should, since we are running out of time in this course, I want to do this program. So let's take 5 minutes break, and you can watch. Those of you who have DS exam, you can drop off, and maybe you can watch it, the video, recorded video. And is it all right? So half an hour. It's a kind of a trade-off that we are striking in the interest of covering more ideas in the course. Okay, so time 11:25. I'm stopping the share. I'll stop recording and I'll start recording again. We will do it 11:30. We will regroup.